So I'd like to do a couple more examples of finding equations of planes. Now remember, to find the equation of a plane in R3, you need two things. You need a point on the plane, and you need a vector that's perpendicular to the plane, sticking straight out of the plane. So let's do this example to start. Let's find the equation of the plane containing the point 214 and is perpendicular to this line. So remember, this is the parametric equations for a line. So here's my answer. I have a point on the plane. That's easy. That's given to me. A point on the plane is 214. I can see from these parametric equations a perpendicular vector. So a vector that's parallel to the line can be found by looking at the coefficients in front of the t variable in these parametric equations. The coefficients in front of the t variables give me a parallel vector to the line. And if a vector is parallel to the line, it's going to be perpendicular to this plane. So a perpendicular vector to the plane, in this case, looks to be 1, 0, 2. So I took the coefficients of t in these three parametric equations. So the plane is now easy to find. The plane is formed by looking at x minus 2, y minus 1, and z minus 4. This is a vector that's parallel to the plane. It's the vector that starts at the point 214 and points to the vector xyz, or points to the value xyz. If I take the dot product of that with my perpendicular vector to the plane, I should get 0 because these two vectors are at 90-degree angles from one another. That means when you take the dot product, you get 0. So the equation of the plane is now 1 times x minus 2 plus 0 times y minus 1 plus 2 times z minus 4, and that should equal 0. I'm okay with you leaving it like this, but sometimes I like to write it out a little bit more. So this is x minus 2 plus 2z minus 8 equals 0. So my plane is x plus 2z is equal to 10. All right, let's do another example of finding a plane. So let's find the plane containing 3 points. So how about I pick the points 1, 0, 0, 1, 1, 1, and 1, 2, 3. There's one and only one plane that contains these 3 distinct points. That's why a camera tripod, has 3 legs, because you need 3 points to determine a plane uniquely. Well, to find the equation for the plane, I need a point on the plane, of which I have 3, but I also need a vector that's perpendicular to the plane, a vector that's sticking straight out of the plane. Watch what I'm going to do. I'm going to take the point 1, 0, 0, and I'm going to subtract the point 1, 1, 1. So I'm going to get 1 minus 1, 0 minus 1, and 0 minus 1 again. This is a vector that tells you if you're standing at the point 1, 1, 1, move in the length and direction you would move to land at the point 1, 0, 0. So in other words, this is the vector that starts at the point 1, 1, 1 and ends at the point 1, 0, 0. That vector is parallel to my plane. If I take any 2 points in the plane and I draw a vector between them, that vector is parallel to the plane. So I could find another vector that's also parallel to the plane by subtracting these 2 points. When I take the cross product of 2 vectors that are parallel to the plane, I'll get a third vector that's perpendicular to the plane. So in this problem, the idea is I'm going to find 2 vectors that are parallel to the plane, take their cross product to get a third vector that's straight, bursting right out of the plane at a 90-degree angle. That will be my perpendicular vector. So I'm taking the cross product, I'm going to subtract these 2, maybe I'll get the vector 0, 1, 2. Now I will cross them. So I write my ijk down. I put this vector in the middle. This is the vector 0, -1, -1, 0, 1, 2. Taking the cross product, the coefficient in front of I hat would be -2 minus a -1. I think the answer is -I hat. The coefficient in front of j, if I cross off the j row and column, the remaining 2 by 2 determinant has determinant 0. So I get 0, 2 minus 0 times -1. 0j, and similarly 0k. So a perpendicular vector in this case is just the vector -1, 0, 0. Okay, so my plane is x. I'm going to pick one of these 3 points. It really doesn't matter which one you pick. In the end, you'll get the same equation for the plane no matter which one you choose. But I'll choose the first one. X minus 1 times y minus 0, z minus 0. And I'm going to dot that with the vector -1, 0, 0. That should equal 0 because this is a vector in the plane and this is a vector perpendicular to the plane. So the equation for the plane would be -x plus 1 equals 0, taking the dot product, or x equals 1. Okay, wonderful.